we want to show that the left-hand side infinite series is equal to the right-hand side function in terms of x, where x is inside this open interval. In other words, can we show that the power series of this function is equal to exactly this form? So it's not easy to directly, straight away, to apply the Taylor series using the nth order derivative of this function nearby 0, at the point 0. So somehow we're going to prove this lemma first. So this definite integral is equal to this. I just treat y as a constant or as a parameter. I integrate with respect to x. Y is inside this open interval. Also, we're going to prove this simple identity, this double factorial relation between double factorial and this single factorial. So first lemma. First, this definite integral 0 to 1. 1 over 1 plus yx times square root of 1 minus x squared dx. X goes from 0 to 1. First of all, we let x equal to sine t. Then dx is equal to cosine t dt. Right, so the new boundaries should become when x is equal to 0, t is equal to 0. When x is equal to 1, t is equal to half pi. And the new integrand becomes, so the dx becomes cosine t dt. Right? 1 plus y times cosine t times sine t times square root of 1 minus sine squared. Right? So definitely this becomes cosine t, right? Positive, because t, there's no negative, no absolute value. 0 to negative, so to half pi, so this becomes cosine t, so cosine t, cosine. So this is actually just dt. So as soon as we see something involves only trigonometry, then we know that it's definitely solvable, definitely integrable. So the question is, how can we somehow rewrite it into, of course, we're going to rewrite it into using one identity, sine square half t plus cosine square half t plus y times 2y. So double angle formula. Sine half t cosine half t. Right, so this way, we divide top and bottom by cosine square half t. Right? 0 to half pi. So 1 over cosine square half t dtw. Because I noticed that I can use the derivative of tangent half t, right, times some constant. And so therefore this should become, divided by cosine square, I have tangent square half t. This becomes 1. This becomes 2 times y times the cosines cancelled out. So tangent half t. Like I said, I noticed that the derivative of tangent half t, is half times 1 over cosine square half t. Right? So in other words, d should be equal to this time dt. Right? So the top can become times half on both sides. Right? Times 2 on. So this time can replace the top with just 2 times tangent. So d twice tangent half t. Later I can use, I can let it becomes u. Right. So if I let tangent half t become u, right, I can see this 2 du. Right. In fact, this tangent square 2y tangent. In fact, when I change when t is equal to 0, u is equal to 0, t is equal to half pi, so this becomes pi over 4. U has to be 1. Tangent pi over 4 is equal to 1. So from 0 to 1. Like I said, 2 du. I just bring up 2 here. Right? Bottom becomes u squared plus 2y times u. Treat y as a constant. Plus 1. Completing the square when that becomes 2, 0 to 1. Right? du u plus y square, right? Then I have to, because this will come out to be u squared plus 2yu plus y squared. So I just minus y squared. So plus 1 minus y squared. Right? Then this should be easy to integrate, right? Because as soon as I let obviously u plus y equal w, right? Equal w. The new boundary should be when u is equal to 0, w equal to y. When u is equal to 1, w equal to 1 plus y. Right? And then also du becomes dw. Right? W squared plus 1 minus y squared. Right? So this time we just obviously I'm going to turn this into 1, so I just extract 1 minus y squared. Right? So extract it out. Right? This will become, so I have to divide by this. Right? So 1 minus 1 y squared. I'll put a square root. Then put w here. All together, I put a square. Right? Then this becomes 1. So now we reached this result. So in order to solve, like I said, this becomes arctangent. Right? As soon as we just can treat this as a whole unit. Right? So let me just pull out the 1 minus 1 squared, because treat y as a constant. Right? So 2 over 1 minus y squared. Right? It becomes arctangent 1 minus 1 squared w right square. So because I have a constant here, right? So I have to multiply by its reciprocal. In other words, square root 1 minus y squared. Because when you differentiate it, when you double check that, right? So that makes it, whose derivative is equal to exactly that. Right? Of course, evaluated from y to 1 plus y. Right? So, and of course, we're going to eventually simplify everything, hopefully. So, arc tangent replace w with 1 plus y. All right, then minus arc tangent square root of 1 minus y squared. Y. Like I said, how do we simplify? The difference of two angles, because tangent is the ratio, right? So arc tangent is the angle. So angle minus another angle. Right? We always have this. Let's say we have the tangent alpha equal to A, right? Tangent beta equal to B, let's say. And we always have tangent A by alpha minus beta. We always have a standard formula, alpha minus tangent beta, or 1 plus tangent alpha tangent beta. Right? Then we can apply arc tangent on both sides. Right? This is the angle. Right? This is the ratio. Apply arc tangent again, so it becomes angle. So alpha minus beta. Right? In other words, alpha is arc tangent A. Right? Right? Minus arctangent B, right? That's alpha minus beta, right? Also equal to arctangent of this, what is this? Right? Tangent alpha minus tangent beta, meaning A minus B, right? 1 plus A times B. Right? So we can simply just say, so the difference between two, so this can equal to that, right? So arctangent something minus arctangent another thing can be written into arctangent combining, A minus B, right? But this is A, this is B. Inside here, A minus B, 1 plus AB, right? Y squared, 1 minus y squared. It becomes just a single arctangent. Right? So you just substitute this inside here, right? So I'm just gonna straight reach to the conclusion. Square root of 1 minus y, square root of 1 plus y. Right? Then we can further simplify arctangent to this thing. Right? I say, because I can just let I just let it equal theta. It's an angle, so which means tangent theta is equal to this inside. Right? 1 minus y squared root of 1 plus y. Then I say 1 minus cosine theta. Right? 1 plus tangent square. And that's a standard formula. right? Equal to 1 plus y, 1 minus y. Okay, that is equal to 1 plus y, and just 2. Right? When you take its reciprocal, I have cosine square theta is equal to half of 1 plus y. Multiply over 2 times cosine theta equal to 1 plus y. Minus the 1 over there, minus 1 equal to y. Right, so what does that mean? Left-hand side is just double angle formula. Right? Cosine 2 theta is equal to y. Right, so which means so arc, right? Theta is equal to arc tangent this thing. Then arc cosine y is equal to the angle 2 theta. Right? Again, theta is, like I said, I let this equal to theta. Right? 2 theta is equal to, right? 2 times theta equal to arc cosine. I simply have 1 minus square root minus 1. I can easily just say 1 minus, so 1 over square root of 1 minus 1 square. Right? Yeah, no problem. Yeah. So this, like I said, arc cosine y. So after solving this integral, I reached something kind of looks like this, except I don't have this. I have something arc cosine instead of arc sine. But if you apply the trig identity of between arc sine and arc cosine, they add up to half pi. Then you can simply reach this conclusion. Now, this is also easily verifiable using the definition of double factorial, right? The product of all the odd numbers starting from 1, 3, 5 all the way up to 2n minus 1. You just multiply this over, right? Then you can easily verify that 2n factorial is equal to this times that. So this is easily verifiable. So to reach this conclusion, first let's look at this integral, same integral, using from a different point of view. Right? So this time the same integral. I say let's use the moment we see 1 over 1 plus y times x, we use the geometric series. Right? Common ratio is minus minus, so negative y times x. That's the common ratio, right? Right, this means infinite sum n goes from 0 to infinity. Because here x and y both inside this is negative 1 to 1, so this is meaningful. Right? So we negative y times x. Right? The first term is 1, so start from 0. Right? So no problem. Yeah. So this doesn't change, right? This has nothing to do with n, so we can easily just put it like that. Right? Then so first we do the summation, then we do the integration. So here I'm going to switch the order of infinite sum and integration. Right? So just a long story short, in this case, it's totally legitimate, justifiable. Right? It has something to do with convergence radius of the power series and the absolute convergence and uniform convergence not in this open interval, but in any closed interval inside this open interval, we have the uniform convergence of the functional series. Right, so that way it's perfectly okay. Right, first, let integration, then we do summation. Yeah. Negative y and 1 minus square dx. So here, of course, we can first fix n, because later we're going to let n change, right? First we do integration, so treat n as fixed. So integrate with respect to x. Y is also can be viewed as constant, right? So perhaps we'll just pull out negative y to the power of n outside, right? So negative y to the power of n. Right, integral 0 to 1. X to the power square root 1 minus x squared dx. Right, so this should be easy to integrate, right? As long as we let x equal to sine t again. So dx becomes cosine t dt. And this becomes n 0 to infinity. Negative 1 and 0 to half pi, because when x is equal to 1, t must be half pi. Right? So this time sine, so x to n, so sine to n, right? Dx becomes cosine t dt, but the bottom 1 minus sine square, right? Becomes cosine square, so cosine at the bottom, so cosine at the bottom cancel with the cosine at the top, so we have nothing with everything. That's all we have is sine to n t dt. That's it. So again, we use the standard form, the Wallis integral formula. Of course, depends on whether n is odd or even. Right? If it's so, we split it into two parts. So, since it's 0 to infinity, right? 0 to infinity. Perhaps I just write it in this way. I say first of all, I start from 0 to infinity. First I look at the even part. Right? When n is even, I can still use n, right? I could use k, perhaps, but I still use n, doesn't matter. So perhaps I start from 2n, right? 0, 2, 4, 6, so I just call it 2n. So when the power becomes 2n, right, I can always have, so I copy down negative y to the power 2n. But I don't need, because it's already even power, so negative doesn't exist anymore, right? So positive. So according to the Wallis formula, right, if the power is 2n, I have 2n at the bottom, double factorial times half pi. Right, with the odd I have half pi, even I have half pi, odd I don't have half pi. So top I have 2n minus 1 double factorial, right? That's Wallis formula. Wallis. And so later I'm going to use this identity. So replace this. And second, so The other part, when n is odd, right? This when n is even. So when n is odd, it's simple. So I can write it as negative y to the power of 2n plus 1. Right? But since now the power becomes odd, so that means it's always going to be negative, right? Negative to odd power. So I can easily just pull out the negative. And then inside here is always positive. Again, n goes from 0. Right, everything positive. Y to the power of 2n plus 1. Our first term is just power to 1. Right? First term power to 0, no problem. If I want to go from 1, I should perhaps write 2n minus 1, but later I'm going to reindex. So in the end, it's going to be the same. So again, Wallis formula. This time the power becomes, like I said, 2n plus 1. So 2n plus 1, double factorial. There's no half pi because it's odd. So 2n plus 1 minus 2n double factorial. Now I'm going to 0 to, I'm going to replace 2n minus 1 double factorial with this thing, just to simplify everything. I just rewrite it. Since it's so y to the 2n, right, copy that down, and again 2n double factorial. I'm going to rewrite it. Right? So 2n double factorial, right? The product of all the even numbers starting from 2, 4, 6 all the way to this number. So I can just pull out the 2 from each number. Each number is even, so pull out the 2's. So how many n many numbers? So 2 to the power of n has been pulled out. All right, what I'm left with is just n factorial, in fact. All right, this is easy. So copy this down. I replace it with that. 2n factorial. 2 to the n times n factorial. Half pi. Right, that's this part. So this actually, right, this becomes 2n factorial, n factorial, n factorial. It's just the binomial expansion coefficient of 2n choose n, right? I'll just separate the 2. This term can be separated out. So when it comes to this term, right, so what happens with this term? Right, this sum, y. Since this is the reciprocal of that, right? Because here the double factorial is the 2n double factorial. Even is on the bottom, but even is at the top, right? Odd is at the bottom, but they differ by 2n plus 1. Otherwise, they would be reciprocal. But here I just rewrite it into, because like I said, 2n plus 1 can be taken out, right? I'm left with just, by definition, 2n minus 1 double factorial. 2n double factorial. Now this time, when you take out this term, this over that should be the reciprocal of just that. Right? Then I just reciprocal this. Right? Replace that with, so n 0 to y to n. Like I said, I just separate this term. So 2 to the 2n, right? 2n factorial, n factorial, n factorial. Simply 2n choose n, right? binomial coefficient. Yeah, times half pi. Later I'm going to combine this term, but for now, like I said, when you forget about this term, right? So this over that, actually the reciprocal of this. Yeah? All right, but this can be written as that. Right? In other words, can be written like this. So all we have to do is to replace this with the reciprocal of that. Right? 0 to y, 2n plus 1. So like I said, copy down 2n plus 1. Replace the remaining with the reciprocal of this. So put this at the top this time. 2 to the 2n. And put this at the bottom. Right? So 2n, choose n. So we finally reached this expression, another way of representation of this definite integral. We know that first of all it's equal to this, but then we represent it, right, in a different way. But so let's just call that I. Right, this I can just copy it down, but this I'm going to simplify, especially this term. 2n times 2n, choose n, and re-index, by the way. N go from 1 later. So 2n times 1, 2n plus 1. In fact, 2n plus 1 times 2n, choose n. How can we rewrite it? First of all, I say 2n plus 1 times 2n altogether factorial, n factorial times n factorial, according to the definition. Now this time, since 2n plus 1 times this factorial already give me 2n plus 1 factorial, but I want to make it 2n plus 2 factorial. Eh? Right, what can I do? I multiply by 2n plus 2. Right, then 2n plus 2. Right, it'll give me 2n plus 2 factorial this time. Okay. So 2n plus 2, I'll just take out, because eventually I want to make up 2n plus 2, choose n plus 1. I want n plus 1 factorial appear at the bottom. So when I take out 2 from this term, right, I'm left with n plus 1. Give this n plus 1 to this n factorial. It'll give me n plus 1 factorial. I copy down this. Right? I still want another n plus 1 factorial. Right, so what do? I multiply by n plus 1. Up here and down there. Now I have another n plus 1 factorial. Right. So in fact, this time 2n plus 2 factorial over n plus 1. See, n plus 1 plus n plus 1 equal exactly 2n plus 2. So this is exactly, I'll just copy down half of n plus 1. Exactly 2n plus 2. Choose n plus 1. Right? The binomial expansion coefficient. So the bottom, in fact, can be written like this. Right? So yep. So first of all, my definite integral. First, copy down this term. Simply combine that two terms, right? Half y to 2n times 2n, choose n times half. Then minus n goes with 0. Y 2n plus 1 times, copy down 2 to the 2n. Then the bottom, like I said, bottom becomes just this. Half n plus 1 times 2n plus 2, choose n plus 1. Right, that's at the bottom. Now, if I re-index, right, so re-index, n goes from 1 to infinity. Right? So n goes from 0. Power should go from 1. So n goes from 1. I should say y to the power 2n minus 1. Right? Then it'll become power of 1. So in other words, all I have to do is to replace each n with n minus 1. Right? That's re-index. Right? Then I say, first of all, I say, perhaps I'll move this 2 onto the top, right? Because I multiplied by 2 at the bottom, cancel this 2. I multiplied 2 at the top as well. So power should become plus 1, right? Then, like I said, I just replace each n with n minus 1. So this simply becomes n, and this, right, 2n, or 2 times n minus 1, 2n minus 2 plus 2, 2n. Right, n minus 1 plus 1, n. Then 2 to the 2 times n minus 1, so 2n minus 2 plus 1, so 2n minus 1 this time. Right. Then I can I can just combine those two terms, right? Because they have the same power, right? 2n minus 1. So 2y right? I'm getting very close. Yeah, exactly equal to, right? You just replace y with x. Right? Right? 1 over n times. Right? That's exactly equal. Right? N goes from 1. Right? So y replaced with x. Same thing, right? 2x power is 2, same power, 2n minus 1. Right? The bottom I have n times 2n over 2. 2n choose n. Right? Is it equal to this side? The question is, right? Right? But this is only equal to this sum. Right? But the whole, so this sum minus this sum is equal to the original integral, right? Well, proven to equal to this. So as long as we can show that, because remember, I want to show this equal to that. In other words, this is just that, right? Let's replace x with y, right? This is exactly so. Right. So to show this equal to that. In other words, to show this equal to that. All I have to show is this equal to that, right? Because this minus that equal to I. This minus that equal to I, right? Is this equal to that? Right, that's my question. Right, if they do, yes, then I can show. Then that means this must equal to that. That's the desired outcome. Right? So how can we show this is equal to that? In other words, how do we know that the Taylor, the power series of this function in terms of y, right? When we expand it, how do we know it is equal to this infinite sum? So all in all, I've just shown that not only this definite integral can be expressed in this way, right? That's already true. We've also shown that it can be also expressed in this way, right? So it looks like this part looks like exactly the same as this part, except we have x here, we have y, right? So if you want to show this is equal to that, in other words, you just have to show this is equal to this. Replace x with y, right? But to show this is equal to this, x with y, right? All you have to show is this equal to that, right? So first of all, it's 1 over square root of, right, can be written into 1 plus x. Power is negative half, right? So that is equal to 1 plus n goes from 1 to infinity, right? Negative half, choose n times x to the power n. Right, that's its power, of course. Right, within this this domain. All right, so we can actually rewrite this, right, this generalized coefficient, right, by binomial coefficient into negative half times every time you just reduce it by 1, right? So then it becomes negative 5 over 2. Negative half of, if you have three terms, you go up to this term, right? So 5 is 2 times 3 minus 1. Right, so 2n minus 1 over n factorial. Right? Then all you have to do is to simply take out the negative 1 of each term, right? N many terms, so negative 1 to the power of n. Then you have double factorial, 2n minus 1. Okay. Then we're going to use this lemma again, replace 2n minus 1 double factorial with this single factorials. Right? Then we can just n factorial negative 1 to n 2n factorial then 2 to the n times n factorial. And of course, you take out the 2 down here, right? Every term you take out the 2, right? 2 to the power n at the bottom, right? So call it 2 to the n. And this time 2n factorial, n factorial, n factorial. Again, 2n choose n, right? Then you just have to, then you -1 2n choose n, then 2 to the 2n, right? So you can actually write this power series like, in fact, we can just combine the 1 into here, so n goes from 0, right? It doesn't matter. So you can -1, right? 2 to 2n, 2n choose n. X to n, right? Because when n equal to 0, you have 1, right? You have 1 times 1, no problem, right? First term 1, so it doesn't matter. So 0 to infinity. So that's the expression when you have x down here, right? But when you have negative y squared, right, then you just replace you just replace x with negative y squared, right? Negative y squared, right? But negative to the power of n, right? Distributed to n, so negative to the power of n cancel out with this negative to the power, so that becomes positive. 2 to 2n, right? You copy down 2n choose n. Right? There's no more negatives. So y squared to the power of n, just y to the 2n. Right? Then somehow you can just combine this term and this term. They have the same power. That's it. You just n go 0. 2n choose n times half y to 2n, right? So that's the power series, y. Oh, y is, yes, in this open interval, no problem. Right? You can express it in this way. So then you just multiply by half. Right? Right, by half pi. Right? Half pi. Half pi. Right? So like I said, we've just shown that this expression, in other words, this expression, right, half y to 2n, right, 2n choose n times half pi, right, infinite, from 0 to infinity. So this part is really equal to this, right? So this part. Right? They're really equal to each other. Right? So like I said, those two combine to be I, right? Same with those two. Right? So this power series equal to this. Right? Then the remaining must be the same, right? Must be the same. Right? You just replace y with x, right? Same thing, same idea.